So, hi everyone, my name is Jing Wang.
My name is Huang, and we're introducing an interesting problem about a rat in a maze. So the setup goes like this. There's a 3x3 maze where the rat is placed in the bottom left corner. There is food in the other three corners. The rat has an equally likely chance of going to its adjacent corners. So in the bottom left, there's a 1/2 chance of going up and 1/2 chance of going right. The rat moves right. Now the rat has a 1/3 chance of going either up, left, or right. If it goes right, it'll reach the food. So the probability of the rat moving to room 3 from room 1 in 2 steps would be 1/2 times 1/3, which is 1/6. That's the probability of that one route. What if the rat were to turn up instead to go to room 7? That would complicate this problem a little bit.
Yes, so similar question like how do we find the probability of the rat finds food in 6 steps? So in one road like this, the rat takes the rat 4 steps to find the food. But if the rat moves crazily, it would take the most 6 steps to find the food in room 9. So indeed, in any room, the most finds the food. Each step, the most move in is dependent to its previous position. So consider this rule. At each step, the mouse has equal probability to go to different room. So this means we can visualize this as a directed graph of the maze. So in each room, the mouse finds the food. There will be a sequence of room numbers relating with the probability. Thus, we can perceive the moving room of the mouse as some sequence of dependent events.
To calculate the probability to that problem, it would be very difficult if we had to consider a condition against all previous events. So we must use a Markov chain. So what is a Markov chain? Markov chain is a sequence of random variables that exhibits one-step dependence, which follows the Markov property. And that states that the past and the future events are conditionally independent given the present. So we only need the most recent state to predict the future state. So if we wanted to go from I to J, normally we would have to condition that against all the moves previously made before I to find the probability of moving from I to J. However, if we used a Markov chain, according to the Markov property, we can ignore that and use only the most recent state that it was in. This significantly reduces computations and makes solving problems with complex distributions much easier. And this is useful in many fields such as finance, AI, sports, to biology, many fields that you can think of. So to visualize these probabilities, we want to construct a transition matrix Qij. The I rows and the J columns represent the rows represent the initial state that the entity is in, and J represents the state that you want to go to. For example, if we wanted to calculate the probability of going from state 1 to state 4 in this diagram shown here, we would have to go to Q14, which we see is 0, and that is the same as the picture. So what if we wanted to calculate, for example, multiple steps into the future, such as what's the probability of going from state 1 to state 4 within 4 steps or 5 steps? We would simply take the transition matrix to the 5th power, and we would get that the new Q14 to the 5th power would be 395 over 1,296 chance of getting there. So now we will go into our simulations to show you our rat problem in R.
So in the R Studio, we construct an interactive program that can tell you the probability of the mouse find the food in certain steps with designated matrix. So first, if you ask like what's the size, enter the size of the n by n maze, let's try 3. So and then you will decide like what kind of answer you want to find. If you want to find the probability the most find the food after equal to or smaller than x moves, you can press 1. And then we can enter something like less than 8, which means it should give us the probability the most find the food less than or equal to 7 steps. So in this program, we do a kind of 10,000 times simulation, and the result is the probability the rat finds the food before 8 steps would be around 77%. And we can also get the mean expected steps for the mouse to find the food would be around five steps, and the variance as well it would be around 12.8 steps. And we can also find the result from the Markov matrix directly. By constructing the Markov matrix 1 through 9, and then by combining the columns 3, 7, and 9 together, we will get a reduced Markov matrix, a 7 by 7 Markov matrix with the probability at each spot. And by replicate to the 7th step, to the Q, which means Q7, and then we will get the new transition matrix Q7, and then by trying to find the probability from going to state 1 to state 7, which means the rat is in the room 1 and go to the food room, we will get a similar probability as what we get from our simulation.
So in conclusion, we can see that Markov chains are very flexible and give a lot of information on probability, and we can calculate some very crazy probabilities. However, it's very tedious to list out its transition matrix in R. It takes a really long time, and you have to calculate a bunch of probabilities beforehand. It's a lot of work. It already cuts down on the workload, but it's still a lot of work to calculate that in R. In comparison to our program, which is much more direct and offers a lot more offers some customizability in terms of scope and scale. We can increase the amount of rooms, or we can increase the amount of steps without having to craft a new transition matrix that's much bigger and much more annoying to craft. So for our future plans, we want to construct better simulation programs by offering more customizability so that it could simulate other problems that besides the maze. So it's more of a template. And we want to find a way to also to generate transition matrices, since that the program is good, but it's not as flexible as Markov chains. So if we're able to find a way to generate transition matrices much easier, we can then use Markov chains more to find the more complicated probabilities. And that's it. Thank you.
Yeah, that's the end. Thank you very much.